Hi there. Welcome to my machine learning project presentation. So my name is Marietta, and this is my data science project, which is about predicting a death outcome from medical data. So the data set represents 299 patients in Pakistan who are already suffering from heart failure. And that's just a bit of context to explain some of the bias that we'll find within the data itself. And a bit of a heads up, I have a lot of slides in here because I want to cover. I'm not going to cover it all in detail. It's there so that if you are curious, you can pause and take a look at it. But just a heads up that I'll be going through it kind of quickly and just give an overview of stuff. So let's get started. This is a broad overview of what I'll be covering. First, I will talk about data exploration, how I visualize the data, and how that helped me make decisions about splitting, about transformation, and other ways of preparing the data for machine learning. And then I'll discuss machine learning itself, choosing classifiers, training the models, evaluating them so that we can compare them to each other and choose the best model. And then after choosing the best model, we train it, or no, we predict the test set on it, and then we evaluate how that does. And then I will conclude with my final thoughts. So first, talk about data exploration. We're visualizing the data to get a feel for what we're working with. So I started by plotting a histogram to get a bird's eye view of everything, just a quick look. And something to point out is that we have 12 features that we're going to be using to predict the death event, which is our target. And the target is the categorical column, which means that we will be using classification models, specifically binary classification models, since it's a binary classification problem. And another thing to note is the age histogram. It has a pretty normal shapes distribution, which I kind of liked. So it definitely caught my eye as something that I could use in terms of splitting the data, especially since it makes sense that like age would be a good predictor of death. So yeah, just started with just getting a good broad overview of the data before anything else, and then I went into splitting the data. So I did this before going into the data in more detail because I wanted to avoid looking at the test set and making decisions based on it, even though I'm not supposed to have seen it yet. So I tried to do the splitting before knowing more about the data set. So like I just talked about, I wanted to do it on the age column. So I turned that into a category, and then I did a stratified shuffle split with the test set being 20% and the training set being 80%. So after splitting the data, then I could dive deeper and discover more things about it. So this is what I discovered. I first started by looking for variables correlated with the death event. And I did a correlation matrix, and it looks like time, ejection fraction, serum creatinine, and age are the top features correlated with death. So I looked at the top one. So time is the number one predictor of death, follow-up time, that is. And so I plotted that to get a better look at it. And it looks generally about, if the follow-up time is less than 50 days, then there is a high likelihood of death. And then I went forward with exploring the rest of the data, the rest of the features that are highly correlated with the death event to get a look at what that is like. I won't really go over these, but just they're there for some context. And then I looked at categorical data, just things that I was curious about and wanted to explore. You can look at that. And this one I will talk about. So I found through the correlation matrix that categorical columns are not very good at predicting the death event. And I was curious about if in combination, like if there's, how many people have combination of some of these risk factors, first of all. And this one down here is just the general, like just the plain counting of the combinations. And this is the same thing, but split based on death event, whether they died or not. And it looks like, it doesn't really tell us much, but what I did get from doing this is that this would be a good feature to add to our data set when I get to the part about transforming the data and adding columns. I think it'd be a good attribute to have a combined risk factors column and see if that maybe does better at predicting a death event than the individual categories themselves. So we'll go to that next. Adding attributes. So like I just said, I'm adding risk factors, combining them, and that's the attribute I'm adding. So I experimented with that before having it in the combined attributes adder. And I calculated the correlation matrix and saw that it does a pretty good job, well, not good, but a better job at predicting death event than the rest of them individually, which makes sense because it's combined. But that was good to see. And so adding attributes, like that's how I decided to do that based on looking at the data and discovering that maybe we could combine the risk. And that's just one part of transforming the data to be ready for machine learning. So this is the rest of that, those steps, the pipeline construction. So the strategy I use to construct the pipeline, I impute just in case. I use a simple imputer. There isn't any missing data in our data set currently, but just in case there turn up some later on, I have that there. And then the second one is combining the risk factors and dropping the others. So over here with the combined attributes adder, I have a toggle for it where I can, after combining the risk factors into one feature, I can delete the individual ones so that it cleans up the noise a bit for the machine learning model. So after this, the pipeline is complete and the data set is fully ready for machine learning. So let's talk about machine learning, choosing classifiers and training models. So I started by looking at classification models in general, and I chose some of them and I fit it and predicted my data with it. And I compared them to see how they worked. And these are my top 5. So I have a logistic regression, support vector machine, decision tree classifier, random forest, and AdaBoost. And basically, I collected all these classifiers, I trained them, evaluated them, and so that I could compare the performance to each other. And these are all classification models, so that's why they're good fits for this problem. So as part of the evaluating the models and comparing them to each other, we have an ROC curve. The original data set, meaning it has the new column of the combined risk factors, but it does not drop the original columns that go into it. Dropped columns, meaning it also has the risk factor combined column, but it does drop the underlying features that go into that. And there is a bit of a difference between the two, but not much. So I'll just focus on this one. And right now, my front runner is the AdaBoost classifier, although it has an area under the curve of 1, which looks good, but also is kind of dangerous. It's like too good to be true type thing, because when you have a score that high, it generally means that it is overfitting, and you have to be careful of that. So in order to test that, for all the models, I trained them, calculated the accuracy score, and then also did a cross-validation, 10-fold cross-validation, and calculated the mean of those scores, put that into a data frame so I could do this relationship plot between the accuracy scores and the cross-validation mean. And I found this was a good way to check for how much the models are overfitting. And like the two bottom here are overfitting quite badly, but still the front runner is still the AdaBoost classifier, which is not as good with the cross-validation mean as it is with the accuracy score, but it's still better than the rest of the models. So that is currently still my front runner. So something else that I experimented with is splitting the data based on time. So time as another one predictor of death, I thought it'd be also a good column to try splitting on. So I experimented with that. And this is the relationship plot that I got based on that. And it's a bit different from the original, which is original meaning using age as the splitting criteria. And I didn't really like the direction it was going in, the numbers it gave me, so I just dropped it and went back to the original using age as the splitting criteria. So after that, AdaBoost classifier was still my top contender, so that is what I chose as my final model. And then now I evaluate or I predict my test set values using the AdaBoost classifier. And now I'm going to compare how it does to the actual labels for it compared to the other models. So for this one, I did a precision recall curve, and you can see that our final model, the AdaBoost classifier, actually performs rather poorly compared to the rest of them. In general, they're doing not as good as they were before when we were evaluating based on the ROC curve. And I think the reason for that is the precision recall curve does not include true negatives. And something interesting about the data is that there are a lot more cases of the no values. So there are more instances of people not dying, people surviving, as opposed to the yes cases where people did die. So our models have more exposure to those no cases and are better at predicting when somebody survives rather than predicting when they die. So if we remove all of those cases of the negatives, which is where they kind of get their shine from, then all the models perform rather poorly. And the models that are more prone to overfitting, like the Adabas classifier, performs even worse because it's good at predicting what it has seen before, which is mostly the no cases, but very bad at predicting a new distribution of data. So something I learned by looking at this decision recall curve is that it would be a good metric to use before choosing a final model, because looking at this now, I'd probably make a different decision about which model to go with as my final model. But I think it's important before choosing your final to use various classification methods to really check for how much it is overfitting and how much it is predicting your data and like how well it does that for different cases. So yeah, and so that's something I learned about that. And this is my conclusion now, and I'll talk about more things that I learned. So first of all, research is very important. There are a lot of technical health stuff in this that I didn't know about before, so I had to research a lot of it. And that's very important for understanding what the data entails. And if you see a pattern, if you see something going on, be able to understand like, oh, this is why it's happening, or this is what that means. So it's very important, I realized during this project, to know like domain expertise in what you're doing the data science upon. Secondly, give it enough time, because this is like it's like growing a forest or something, very complex process, and you have to give it time to work different things out, try different things, let it grow into itself basically. And so that's important to like give it time to breathe as you work on it. And third is to run correlation before anything, because at first I was just exploring the data randomly to see what was there before I actually ran the correlation matrix. But I realized that running the correlation matrix beforehand will give you a better idea of what to focus on, like better predictors for the target column. So especially when you have a very large data set in terms of features, you don't get distracted by other things, and you can just kind of more quickly and easily get up to speed of what you need to be keeping track of. And overall, I had a great time working on this project. It was very interesting. I loved experimenting and trying different things and just trying to see like what will make it better, what will make it worse. And it was a lot of fun to figure it out and get the actual results from this. I love how this works and how cool it is to get insights about things. So with that, we've come to the end of my presentation. Thank you for watching. I hope you understood it and enjoyed it. And also want to say a big thank you to Professor Lee for a great semester of class. I've learned a lot. And yeah, once again, thanks for watching, and I hope you have a good one. Bye.